So good afternoon to you all. And on behalf of Jawaharlal Nehru Planetarium, I extend a very warm welcome to all of you in the audience, and our special welcome to the speaker of the day, Professor Samuel from Raman Research Institute. As you can see, the topic is very interesting, black holes and steam engines. So I don't think you would be in a mood to listen to more of the formal things. You'd be waiting to listen to him. So once again, I welcome you all to this program, and I request the director of ICTS, Professor Gopakumar, to welcome and say a few words about ICTS, and then we'll start with the program. Professor Gopakumar.
Thank you, Dr. Madhusudan. And welcome again to everyone on this nice afternoon for lecture. Most of you have been here, I think, for many of our KAAPI with Curiosity even, so I don't need to tell you very much about them. Even ICTS is perhaps now getting familiar to people, but we are located in North Bangalore in Hesarghata, and in addition to our research and the many events we organize, outreach is something we take very seriously. So we've had a number of public lectures both on campus and then this KAAPI with Curiosity event, which happens every month. So quite coincidentally, day before yesterday, we had a lecture on black holes and the structure of space-time on campus. But today we will, I think, hear a different view from Professor Samuel and related to even the physics of the 19th century on steam engines. So KAAPI with Curiosity, it covers a vast variety of topics, and black holes are just one of the many. We have had talks in biology, we have had talks in mathematics, and so on. So those of you who are here for the first time, please check out all the earlier lectures on our YouTube channel. So anyhow, it's my pleasure to welcome Sam here for our event, and I will now invite Professor Rukmini De from ICTS to introduce the speaker. Oh, by the way, after those of you who have just come in, there's a small surprise for today's KAAPI with Curiosity. On Friday, we launched at the public lecture in ICTS a small book by Professor Niels Andersen from the University of Southampton called The Gentle Wizard. I see some of you have already picked up copies of it. Professor Andersen has written this book to try to convey to the popular, to the lay audience, some of the ideas of black holes and curved space-time and so on through a story about a small boy who goes and makes friends with Albert Einstein and spends afternoons with him, and he tries to explain some of these concepts. And Professor Andersen has been very generous to send over a number of copies of the book for distribution at our public events. He himself gave an Einstein lecture at ICTS about a year ago, so he has been very kind enough to send over copies. So please pick up one per family so that more people can get a chance to read the book. So if you have not picked up the copy after the lecture, they will be available outside over there. So thank you, and I'll now invite Rukmini.
Hello, good evening. It's a great pleasure to introduce Professor Joseph Sam to us. He's currently a faculty in RRI. He got his PhD at IISc and worked under the supervision of Professor Mukunda on constrained Hamiltonian systems, and he has been a faculty in RRI ever since. In the late 80s, he spent some time in Syracuse and University of Utah. His professional interest is very vast. He has worked on constrained Hamiltonian mechanics and symplectic geometry, geometric phase in quantum mechanics and optics, general theory of relativity, quantum gravity, geometry and physics of soft matter. This is very interesting, DNA elasticity, DNA membranes, and so on. And he's currently working in quantum information theory and gravitational decoherence in quantum theory. He loves to keep in touch with mathematics and experimental physicists, and he's very vast in his scope, and also he's very interested in popularizing science through lectures and articles. And he likes to relax and cooks great appam for his friends. So it's a great pleasure to have him here to deliver this wonderful lecture. And you can see a lot of demonstrations are waiting for you. And right now I would invite Rajesh to present him with a memento.
Yeah, I'm very happy to be here and happy to see all of you. I like to share my excitement with science with other people. And I'd like to thank the ICTS and the Planetarium for giving me this chance to talk to you. So acknowledgements are due to Rukmini, Ajit, Amit, Vijay from the KAAPI team, Juni, Anupam, Arun, and Rajesh and Spenta from the ICTS for having the foresight and the vision to put up events like this. And from the Planetarium, the director, Pramod Galgali, and Madhusudan, who's been very helpful to me in setting up my demos. Yes. Okay, let's get to this topic. So on this picture, you see two objects. One is a black hole. It's generally considered as a light trap. Just like you have a mouse trap, a black hole is a light trap. So this is a picture of a black hole somewhere. It's an artist's imagination, actually. So right in the center here, there's a little black hole. I mean, there's a tiny black hole. And it's taking matter from this enormous star. And the matter is flowing around here. And in the process of going around several times, it gets hot because of friction. And it puts out an enormous amount of energy in these two directions. So that is one object, a pretty exotic astrophysical object. And on the left side, you have something that looks completely different. It's a steam engine. It converts heat into directed motion. Now, the steam engine was the mainstay of the Industrial Revolution in England, and you could have found it not just on the railways, but also in the satanic mills of Lancashire and Manchester, where it would be used to power the mills that produced the cloth that was taken from India and returned. That's another story. Okay, so this converts heat into directed motion. That's the surprise about it. And it's not just England and the Industrial Revolution. It actually goes back to Nehru of Alexandria, who had made a steam engine. But that's much earlier. So these two objects look pretty disparate to the average untrained eye. But the connection between these two is very real, and that's what I'd like to convince you of. So if there's one thing I want you to take home from this talk, it's the connection between black holes and steam engines. Now, this lecture is in some ways a tribute to Stephen Hawking. So he lived from 8 Jan 1942 to 14th March 2018. Now, I like this picture because of three reasons. One is that it's not the picture that you usually see of Stephen Hawking slumped on a wheelchair. This was in the early stages of his disease. And you can still see some of the, the slightly unnatural posture of the hand. So the disease was beginning to trouble him even at this time. But nevertheless, the second reason is that this is the time during which a lot of this work, this famous work, was done. The third reason for putting up this picture is that it shows the woman, Jane Wilde, who stood with him, who stood alongside him. And it was because of her, to a large extent, that all this work was possible. Now, Stephen Hawking worked on cosmology, black holes, quantum theory, and the style of work is mathematical relativity. Now, mathematics is a subject that often puts barriers between people. Many of you studied mathematics at high school, and when you left high school, you only retained that part which was useful in your everyday life, and you forgot the rest. The advanced algebra that was forced on you at school, most people leave school and forget about it, and they feel much better after they've forgotten about it. Yeah. I would like to address this talk to the general public. So I'd like to take a poll. By general public, I mean people who have not studied physics beyond high school. So how many people here are of that category? Please put your hands up. Okay, not that many, but I'm still going to address it to them, because I think if they understand it, everyone will. I think that, yeah. So in order to put across the ideas without using equations, I've had to put everything in a slightly different format, and that's what I'll explain next. Well, this is a cartoon by my daughter, Roshni Samuel, who's in the audience here, done when she was about 8 years old. And it shows one famous equation that everybody knows. So this is the only equation which I'm going to use. And I want to convey not just the excitement of the subject, but also some of the substance. And it's true, I'll have to make a lot of compromises in doing so. So it will be far from complete. But the main point is I want to get some basic ideas across. So I will use pictures like this one, words, the kind of things I'm telling you about, demos, which are all over the place there. And most importantly, I will use analogies. Things that look like other things can be used to understand the first thing. Okay? I'll apologize to most of the audience who probably came here wanting to get some equations and stuff like that. Most of you, well, anybody who wants can write to me afterwards, and we can maybe have a discussion about such things. But this is a public lecture, and I want to address it to the public. Now, everything hinges upon the speed of light. So light and sound are the two senses which are most important to us. Oh, by the way, I should also clarify that elementary questions are most welcome throughout this talk. I don't mind if I don't get to the end, if I have to cut out some things. So please feel free to ask questions, especially elementary questions. On the other hand, I see a number of my scientific friends here. I'm going to be rude to them and ignore them completely, because I would prefer to keep the level where most people can understand it. Okay, the speed of light is an enormous number. It is 300,000 kilometers per second. Now, light and sound are the two senses which are most important to us. Through light, we learn to read, and through our ears, we hear, we can talk to each other. These are the two organs which are most important to us. So the whole lecture actually is based upon an analogy between light and sound. So I'm going to make use of the fact that both light and sound are waves. And that is going to put across a lot of unfamiliar ideas in familiar language. Okay, let's talk about the speed of light. It is extremely large. There was once a time when you could go around the world in 80 days, Jules Verne and all that. These days, you can go around the world probably in 80 hours. But light can do that in the blink of an eye. It can go 7 times around the Earth in a second. In 1.5 seconds, it can get to the moon. And I've persuaded you that the speed of light is very, very large. 300,000 kilometers per second. And this speed is an upper speed limit to all speeds in the universe. There's nothing that can go faster than light, nothing that we know of. But now let me get to a different point. When you go out of the Earth, where we all live and die, light takes 8 minutes to get to the sun. Now, that's not a small time. It takes a long time to get to the sun. It takes 10 hours to get to Pluto. Imagine if you were standing on Pluto and waiting for a message. My God, when is that light going to come? Why is light so slow, you would ask. So it's like waiting for a slow train somewhere and cursing that train because it does not come. So 10 hours is a long time to cross the solar system. It's 4.5 years to the nearest star and 3 million years to Andromeda. And you know, there's some light sources in the sky where the light left the source when dinosaurs were on the Earth. It took that long to get here. So I've convinced you then the speed of light is very, very small on a cosmic scale. So do I contradict myself? Very well then, I do contradict myself. Speed of light is both very large and very small, depending on the context. So that's exactly what relativity is about. So relativity acknowledges the finiteness of the speed of light. If there's a speed limit, let's suppose that there's a speed limit in this town which says that nobody can go faster than 100,000 miles per kilometer. Nobody will bother with the speed limit because you cannot even attain that speed limit. So in our normal lives, we put this number to infinity and get on with our lives. It's very well that we do that because relativity is not really needed in most of everyday life. But there are many situations where it is needed, and that's why, I mean, it's very real situations where it is needed, and that's why we have to understand the theory of relativity, both special and general. Now, the fact that the speed of light is very small cosmologically means that the further out you look into space, the further back you're looking into time. So you're basically doing archaeology. You're seeing the universe as it was in its infancy. And that's why the study of cosmology is so important to us. Now, here's a small, a small spiel on analogies. It's a way to relate new things to familiar ones. Analogies are never perfect, but they're almost always useful. Everyone uses them. We use similes, metaphors. Poets use metaphors. For example, they'll say, my love is like a red, red rose. That's an example of a simile, I think. Doctors will say, okay, the body's immune system is like an army trying to fight external forces. Lawyers will say, this case is like that case. Everybody uses it. Investment bankers use it. And sound is very much like light. There are differences, but we can learn even from the differences between sound and light. Both travel at a finite speed. Both have vibrations at a certain frequency. The pitch of sound is like the color of light. So I'll just give you an indication. This is the pitch of sound, which I can... The high frequency and the low frequency are two pitches of sound. That's what I mean by the pitch of sound. And that's very much like the color of light. For example, this thing here is blue, and that has a shorter wavelength. It's very similar to sound in many ways. The color is like the pitch. Now, sources of sound are many. You can hear thunder, voices, you can annoying horns on the road, musical instruments, and depending on how well they are played, it's either annoying or not. The sources of light are lightning, tube lights, the sun. But finally, it's always disturbed atoms that produce light. Fundamentally, it's disturbed atoms either in the tube light or on the surface of the sun. So I'll now show you some demos. And the main point of these demos is that if you take any object which has got a finite size like this one, and you tap it, you hear a very specific sound. You can tell the difference between this sound and say, okay, and say this one. The set of frequencies is very specific to the object. So the set of frequencies that you hear from this is called the spectrum of that object. And it always happens that the spectrum for a closed, something which is confined, is discrete. So I'll give you an example with this flute. This is a flute, an Indian bansuri. And if I close all the holes, I've got a tube. And there's a blowing hole here, which produces all possible frequencies, white noise. When I blow into this, you'll nevertheless find that only certain frequencies are possible here. Where's the slinky? The slinky? Is it, okay. So I'll just show you on the flute that with all the holes closed, I can get about 4 notes without moving any of my fingers. So it's basically sa, sa, pa, sa. 1, 2, 3, 4. The ratios are 1, 2, 3, 4. The few lowest notes here. Now I'd like a volunteer to come forward. Yeah? Okay. So you hold this over here. And this is also a wave. So you just hold it still there. So this is the fundamental, right? That's like the first sa. And then if I do it faster, I can set up. This is the second harmonic. And then if I go further, I can do the third harmonic. I'm not very sure I can do it right now. But you can do it with a little bit of patience. So the modes of vibration of the slinky are basically the modes of vibration of air in the tube. So you can get the first, you can take a seat, yeah. The first 4 notes of the flute. And you notice that they're equally spaced. Now, that is not true of other things, like this bell. You don't have equally spaced tones, but you nevertheless have a very definite set of tones. And actually, I'm sure that you've all encountered this in the kitchen. When you have a vessel like this, it's got a particular tone. You know which vessel was dropped when you hear it. Now, the same thing is true. The same thing which is true for musical instruments and other sources of noise is also true for atoms. An atom is an electron. For a start, let's take just the hydrogen atom, a single proton in the middle, and an electron going around it in waves. So an atom is like a box for the electron, and the electron is a wave in the box. So other waves in the sound wave in the flute is just like the electron in the atomic box. And that also has a specific set of frequencies. It oscillates only at certain frequencies, and it oscillates only when perturbed. Like if I don't blow the flute, you don't get a sound. Similarly, if the atom is left to itself, it doesn't produce any light. You have to excite it in some way, and then it produces light, but it only produces light at a certain set of frequencies. These frequencies are very specific to the atom. Now, I'll show you a demo with light here. So what I'm going to do is to okay, I've got it. So I'm using these Q-tips. Q-tips are things that many people use for cleaning their ears, although it's not medically advised. In fact, the medical advice is that you should put nothing into your ear which is smaller than your elbow. But most people disregard it. So what I do is I dip this Q-tip into water, and then I pick up some salt, common salt here, and there's copper sulfate here. Common salt, as you all know, is sodium chloride, and that produces a yellow kind of flame. Right? You saw that? Okay. And the other chemical I have here is copper sulfate. I just use the water to pick up enough of the substance. It produces a brilliant green. It's clear that the spectra of different atoms are different from each other. Yeah? So astronomers can recognize the spectrum of an atom as well as you can recognize the voice of your friend. And if the signal is coming to you from very far away, they know exactly what atoms are there by assuming that those atoms are very similar to the atoms that we have here. So astronomers get a lot of information about the universe from looking at the spectra of atoms. Now, where's my... yeah. Is not the one? Oh, thank you. That's, yeah. Okay, so it's like an atomic fingerprint. The spectrum of an atom is like its fingerprint, and this demo just shows you exactly how it works. Each atom has got a distinct spectrum, and from that you can recognize the atom. And you notice it's only the positive ion that contributes to the spectrum. So maybe you should think about why the negative ion is not responding here. That's something for you to think about. So next demo I'd like to show you is that light from moving sources is shifted in frequency. Now the speed of light is so large, and my means of moving with a high velocity is so low that I can't possibly show you the demo here with light. So I'll show it to you with sound. So here again, I need another volunteer. Maybe I won't have you again. I'll get somebody else from the audience. Yeah. But by the way, are there any girls who volunteer? It's always guys who volunteer. Yeah, come in. Yes, please. So I just need you to hold this. So yeah, you hold this and stand there, yeah? And take a look at the, okay. So this is a demo that shows the Doppler effect with sound. It's a demo that can be criticized, which is why I've got a backup over there. And actually, it's a dangerous experiment, because if I lose my grip on this bag, it's going to fly into the audience and kill somebody. Yeah? So I'm the safest person in this room, actually. Okay. Yeah, no, if you point it away, they won't see it. They'll have to take your word that it's actually happening. Just, yeah. Can you see the frequency changing? Yeah. Yeah, no, then if you turn it around, it won't really register. I don't know. Well, does it register? It does. Okay, okay, okay. Okay? All right? I think that's enough. Yeah, thank you. Actually, when I showed you the demo just by itself, there's always the suspicion that your brain is playing tricks on you. Are you really hearing it or not? That suspicion can be removed by just appealing to something objective like a mobile phone. And these days, everybody can download a free app from the internet and check for the Doppler effect on their own. It takes nothing but a cloth bag that you can buy from Nilgiris at 6 rupees and your smartphone, which you anyway already have. Okay, so I'm going to now invoke the analogy between light and sound to say that there must also be a Doppler effect for light, which is to say that the spectra of atoms that comes to you from distant parts of the universe is going to be redshifted. That is to say, shifted towards the red end of the spectrum compared to the original frequency. So light shows a Doppler effect. There's a cosmological redshift, which has been known since the 1920s due to the work of Edwin Hubble. Now, the speed of light is nature's speed limit. If you disregard the speed limit as being very large, we end up with what we call Newtonian physics, which is the everyday intuition that all of us have about the world around us. When you acknowledge the speed limit, we come up with Einsteinian physics, which is a completely different way of looking at the universe and at space-time. Okay? Now, it takes a bit of mathematics to understand that, but I'm trying to dilute the subject and give it to you in a form that you can readily absorb it. Most of this talk will just stay Newtonian, and we will use the speed of light to be finite, which is actually not very consistent, because if you are in a Newtonian framework, you can keep adding velocities and exceeding the speed of light. But nevertheless, you can learn a lot from this Newtonian picture. We have already seen that atoms emit photons, or particles of light, and the energy of the photons is related to their frequency. There's a constant relating the energy of the photons to their frequency. High-frequency photons are more energetic. Okay, this is just a brief recap of the relativistic theory of gravity, which was put forward by Einstein in 1915. Once you admit that C is finite, and also the same for all observers, those are the two things that go into the special theory of relativity, you end up with special relativity, and it changes the view of space and time. That already happened in 1905. In general relativity, okay, before we get there, what this does is makes us think that there's not that much difference between space and time. They're just the same kind of stuff. Sometimes we call it space, and other times we call it time. There's not that much difference between matter and energy, and you can convert matter into energy and energy into matter, and it's happening all the time. In the sun, there are reactions going on at this very moment which convert matter into energy, and the sun is losing mass, according to the formula E equal to mc squared, which you saw in the cartoon. Now, in general relativity, this is already true even in special relativity. When you come here, you find that you have to take the same idea and make a very slight change. You use the same kind of ideas that you have in special relativity, but you say instead of being flat, that the space-time is curved, and you get to describe gravitation. It's a remarkable theory, extremely beautiful, and it's been studied for a long time, and right now we're seeing some of its successes coming out. So I planned the talk so that the introduction is about 20 minutes. Black holes, I'll just spend, and I've just finished about 20 minutes. Black holes will take 15, steam engines 5, and I'll make an apology to relativity by saying a few words about it. and finally come to Hawking's work and end with the conclusions. I'd like to pause at this point for questions before we move forward. And also so I can drink some water. So it's all very clear, is it? Okay. So let's understand the role of black holes as traps of light. This story started a long time ago, but let me just recap it. There's the notion of an escape velocity. If you throw a stone up into the air from the ground, it'll go up to a certain height, and it'll come back down. Suppose you put in more and more energy as you throw it up. It'll go higher and higher, and then it'll come down. So the maximum you can throw a stone is probably like 10 or 20 meters. I don't think one can get much further than that. But if you go to the volcano, which is erupting right now in Hawaii, huge boulders are being thrown up to an enormous height of 1,000 meters or something like that. So in principle, there is nothing to stop you from throwing a stone at such a high speed that it will not come back. That speed is called the escape velocity. Actually, the escape velocity is a misnomer because it should have been called the escape speed. It doesn't matter which direction I throw the stone, it will get out if it has got enough energy. So if I drill a hole through the earth here, all the way through the earth, and throw a stone down with the escape velocity, it will get out to infinity. So the escape velocity is the minimum speed needed to get out to infinity. And it should have been called the escape speed, but it's called the escape velocity for unknown reasons. And we now have the suggestion that if the escape velocity is the same as the speed of light, then light cannot escape from that body. So that's the notion of a black hole. In order for this to be true, you have to take the whole Earth and compress it to the size of 1 centimeter, which is roughly the size of your thumb. Or if you take the sun and reduce it to 3 kilometers, you have the same effect. So then the Earth would form a black hole if it was 1 kilometer in, 1 centimeter in radius, and the sun would form a black hole if it was 3 kilometers in radius. Now, this argument was actually given by John Mitchell, Reverend John Mitchell, a clergyman in England. And he was a remarkable man. He has got contributions to seismology and even to gravity. But this idea of his, he received no credit for it at all because it was so far ahead of its time. John Mitchell actually put forward the idea of a black hole in 1783. Laplace followed it up in 1799. And there the matter lay for a whole century until Schwarzschild discovered a solution of Einstein's general theory of relativity, which actually represents a black hole. It represents a non-rotating black hole. Unfortunately, people were confused about what the solution meant, and its significance was not noticed at the time. Then in the 1930s, Chandrasekhar, on the ship from India to England, realized something about the stability of stars. Stars normally burn fuel, and the fuel keeps them hot. And the heat generates pressure, which makes them fight gravity, which allows them to fight the force of gravity. Gravity is pulling them in. So the star is basically a balance between gravity pulling them in and pressure pushing them out. When the star has exhausted its nuclear fuel, there's no pressure left to fight gravity. So it keeps contracting. It keeps contracting until it reaches a stage where the electrons, due to the uncertainty principle of quantum mechanics, have a slight bit of motion, and that motion is enough to apply pressure to fight gravity. So that equilibrium is called a white dwarf. Now, what Chandrasekhar noticed is that if you keep compressing it, if you keep increasing the mass of the star, at some point, these electrons, which are giving you the pressure to fight gravity, they are limited by the speed of light. And once they're limited by the speed of light, they cannot move any faster. And that results in they're not being able to fight against gravity, and the star collapses. So Chandrasekhar had noticed that there was a maximum mass for white dwarf stars. If you put more mass onto a white dwarf star than the allowed limit, it would collapse to form, he didn't know what it would do, but he said it would collapse. So the degeneracy pressure, which is the force from quantum mechanics, is unable to withstand the force of gravity. Now, it was done in 1938, there's a B. Datta in Calcutta, a student of N.R. Sen, and he studied spherically symmetric collapse. So the title of this part of the talk is an idea delayed. That is an idea which has been around for a long time, but it's been delayed through several quirks of history. So Datta noticed that I could take spherically symmetric collapse, and it would actually form a black hole. although he didn't know what a black hole was, he realized that there was a solution like this. And he used some techniques which have been very rediscovered much later. Unfortunately, after doing this work, 2 years later, he died on the operating table, and the work here came to an end. A year later, Oppenheimer and Snyder in the US did the same calculation. After that, the Second World War broke out, and everybody who had any scientific bent was put to work on the war effort, including Oppenheimer, who worked on the Manhattan Project. After the war was over, when people were beating their swords into plowshares, the radar technology which was used to detect airplanes in the war was turned up into the sky to look at the galaxies. They discovered that the galaxies were emitting radio waves. And because of dust in the universe, you can't see too far if you look out. But in radios, you can see clear through to the end of the universe. And we were able to make a lot of discoveries about the universe, about distant galaxies because of radio astronomy. So this idea was delayed through a combination of historical circumstances. I should also say that, Chandrasekhar's discovery was delayed because of Eddington's prestige. That's another story also. Okay. At some point, the radio astronomers discovered that there were very energetic sources of energy in the universe. Energetic sources in the universe, they're called quasars. They look like stars, but they're really at a cosmological distance, which you can tell by looking at their spectra. And they're so huge. I mean, they put out so much energy, but the size is very small. It's just one light day, no bigger than the distance from here to Pluto. It's hard to imagine how such a small object can put out so much energy. And then it was realized slowly that black holes are the best explanation for putting out so much energy. So we'll come to that as the next topic. So it's very easy to understand why black holes are good sources of energy. Remember, when we talked about escape velocity, you had to give energy to the particle so that it could escape from the gravitational field of the Earth. Conversely, if you reverse the arrow, you can send the matter from infinity, let it fall, and it will accelerate to something like the speed of light. Then you can convert that into heat, and heat is energy. Yeah? So that's the reason that black holes are good sources of energy. So here's how an advanced civilization you put a black hole to working for us. Suppose I'm an advanced civilization living on this green planet, but I don't want to pollute this green planet by having dams and things like that. I find a friendly neighborhood black hole, which is over here, take a weight, and I gently lower the mass into the black hole. As I lower this mass, I can use it to lift up a weight here. That weight could be, if you like, water being lifted up in a hydroelectric dam or something like that. And I can store the energy that comes from this mass. The mc² energy can be completely stored here. Now, if I were to just drop it in, I would waste that much energy. And if I were to let it fall in and rub against itself, that would generate heat. But I want to get useful energy. So this is a way of getting very cheap energy by just lowering mass into a black hole and using that energy to lift up other weights. Now, in principle, this can extract 100% of the energy of the mass, 100% efficiency. All the mc² can be converted into energy. But in astrophysics, the efficiency is only 5%, but that is still much better efficiency than nuclear reactions, which are only like 1% efficient. So this gives rise to the subject of relativistic astrophysics and relativistic cosmology. And as I said earlier, this word just means that we acknowledge that the speed of light is not all that big. It's something finite. Okay. Now, a little bit more on black holes. I want to show you that, well, I'll just show you the sound of, suppose I were to take this box. Okay? And throw it down a black hole. As it moves away from me, it will pick up speed, velocity. And so I would expect that the signal I get from the object would be Doppler shifted. So I'm going to show you a demo which shows this effect. Of course, it's a computer simulation. I mean, it's a computer, whatever the right word is. Yeah. So first I'll play you how the source would look. This is a source at some 2 kilohertz. Annoying sound. Okay. Now, if I were to throw the same object into a black hole, it would sound like this. First, you'll hear the same frequency, but the redshift will slowly take over. It will go below your threshold of hearing. So very low frequencies came at the end. That's all the Doppler shift. Yes. Yeah, ask the question.
The previous slide.
Yeah.
Like that conversion E equal to mc square when you drop something into a
Black hole, yeah.
black hole. So how is the conversion to mc square happening? Is not like a potential energy thing.
Yeah, I'll tell you. Yeah, can you repeat the question? Just give me a mic and repeat the question.
Yeah. So question is this: when we are dropping something to a whatever be like black hole or anything. So what the energy we are getting is mg square.
Yes.
But what is shown there is mc square.
Yeah, sorry, mv squared versus mc squared, is it?
No, like see, it's when we drop something to a black hole.
Yeah.
So I have some weight in my hand.
Yeah.
The energy will be like the potential energy.
That's
but
right.
this is an equation where like the mass is converted into energy.
That's right. Yeah. So I'll answer that. He's asking, normally when you drop an object in the gravitational field, you only pick up the energy corresponding to the potential energy. So it turns out that the potential energy difference between the mass at infinity and the mass just at the horizon is equal to mc squared. Because that's the amount of kinetic energy which you had to give. You have to put, you have to accelerate that object, you have to give enough kinetic energy so that it could escape to infinity. That kinetic energy was mc squared. So that's what you're getting back now. So the potential energy difference between here and there is mc squared, and that energy is all you're getting, and you're going to take that up, use that to store it on the Earth in some form. You can store it in batteries, for example. Yeah? Any more questions?
Hi, right here. I'm at the back.
Yeah.
I want to know how exactly the light gets escaped at the accretion disk region.
The light escapes. The accretion disk region is outside the black hole. So the event horizon is over here, and the accretion disk is outside it. So light from here can escape.
Okay.
It will be redshifted, but it can escape.
Okay, what would be the temperature of the accretion disk?
I'll tell you, the light comes out at X-ray frequencies, which corresponds to temperatures of, 1 keV, a million degrees or so. I mean, yeah, I think it's 1 million degrees, I think.
All right, okay.
Yeah, no, I'll give you a better number. Like, I can convert it. See, 1 electron volt is 10 to the 4. Is a million?
So probably more like tens of thousands.
It could be around 3000 Kelvin or something.
Sorry?
It could be around 3000 Kelvin or something?
No, much more than that. No?
6000?
No, X-rays have to come out. It's at X-ray temperatures.
All right.
And X-rays are at 1 kilo keV. And okay, the sun is at 6,000. So you have to multiply that by 1,000. Okay. So, yeah, 6 million degrees.
Okay, and this is for the non-rotating or the rotating black holes?
Actually, most black holes in the universe would be rotating.
Okay.
Yeah, because they are matter's falling onto them, and the matters have got angular momentum. And when it falls into the black hole, you do get angular momentum. So most of the time, we talk about rotating black holes, which have an angular momentum.
Okay, and when would be the actual process of something called as spaghettification takes place?
What?
Spaghettification. It's like breaking down of the particles, any particle or any body that enters into the region of the black hole and then breaking down.
Yeah, no, I don't know that word, but what you're talking about is tidal disruption. There are tidal forces that can pull apart anything, so it can pull apart stars. We'll come back to this point a little later.
Yeah, sure.
Okay? Oh, I'm sorry.
So in the previous slide, I didn't understand the concept which you were trying to explain. Like, you put a weight into the black hole, but then it'll rotate around the black hole and then it'll get heated.
Yeah, I've taken, for simplicity, I've taken a Schwarzschild black hole and I'm lowering it straight into the black hole without throwing it to the side. If I throw it to the side, you're right, it'll keep rotating around like a planet goes around the sun. Yeah? And it'll take a long time to fall in. Yeah? But I'm just lowering it very slowly, like as if, like for example, if I were to take this thing, just lower it gently like that towards the, yeah?
Efficiency is 5%.
Yeah. That was for the astrophysical context. There's nobody actually extracting the full energy content of the mc squared, so we're doing it inefficiently. matter from the star is falling in, and the energy is being converted into heat, redshifted, all kinds of things are happening. So that efficiency is 5%, which is a very high efficiency for astrophysics, because nuclear reactions have only 1% efficiency.
Can I ask another question?
Yeah.
At the back. Yeah. Since you said elementary questions are welcome, you said something about digging a hole inside the earth and putting a stone or a ball.
Right.
So I just want to know whether you dig a hole right through the earth, is it going to come back the other side, or is it going to pop up right back at you?
It'll pop right out on the other side. From energy conservation, you can see that if you drop it from here, it'll go clear through to the. If you just drop it from here, it will go there and come back. But if you drop it with a high speed, it'll go there, it'll overshoot and go off to infinity. If you send it with the escape velocity from here, it will escape to infinity. That's the point I was making. If you just drop it from here, it will just go to the end of the earth. It'll go to probably
center of the earth or the end of the earth?
All through the center and to the other side, somewhere in Argentina.
Oh, okay.
Right? And it'll come back to me in Bangalore. Yeah. I don't know the exact antipodal point to Bangalore, but somewhere in South America, I guess. Okay. Because I've just dropped it. I've not shot it. If I shoot it, it will not come back. There are two experiments. One is where I just drop the ball, then it goes there and comes back. It'll take 90 minutes to come back. But if I shoot it, it'll never come back because it'll go out to infinity from the other side. I hope this is clear. Yeah.
I think it goes in a simple harmonic motion.
Yeah, if you drop it. Yeah, if you drop it, it goes in simple harmonic motion with a period.
It turns up and down.
Exactly, with a period of 90 minutes. Yeah?
But won't it hit the side of the hole because of the Coriolis effect if it's anywhere except for the hole?
Oh yeah, I was ignoring rotation. Very good question. I was ignoring rotation. That's true. Yeah. My God. You should be here. Very good question. Okay. Now, I showed you what happens to a source of sound. But actually, I showed you the sound version, but it could have been light also. A person emitting a fixed frequency of 2 kilohertz. That's the way it would sound if you converted it into sound. That's the demo I showed you. But what happens to him? What happens to a person falling into a black hole? By the way, I should also mention that black holes are great for criminal activities. If you want to commit a crime, and if you want to get it to the body, for example, just find a black hole and put it there. No one will ever be able to discover it. And also, if you're really smart, you can also extract energy from it and sell it on the market. Okay. Now, I want to take a look at the inside view. Suppose somebody is forced into a black hole, like you're thrown in. You don't have a choice. What do you see? First, when you fall in, you don't see nothing much. You cross the event horizon, and you won't even notice it. If you take a solar mass black hole, for example, you cross the event horizon, you will notice nothing very serious, except that you're falling. But at some point, you'll start to feel that there's a tidal force on your body. That is to say, your feet are, let's say your feet are pointing towards the black hole and your head is away. Your feet are pulled more strongly than your head, and you're being stretched this way, and you're being compressed sideways. Now, these kinds of forces applied to a body were last seen during the Spanish Inquisition. People were tortured on the rack. It's exactly like that. It will be very painful when you fall into a black hole. Your head will be pulled away from your legs, and your body will be compressed. As you go a little further, closer in, at some point you'll die. So let's just talk about the physics and forget about the biology. So you get closer in, you find that parts of your body are ripped apart from each other. At some point, the cells in your body are ripped apart from each other. A little further down, the atoms and then the nuclei are ripped apart from each other. So this is a stage at which normal physics breaks down. We don't know what's going on because everything is being ripped apart from everything else at such a high rate. Yeah? So that's the end of physics as we know it. It's a bit like what the Vikings used to say about the Earth. If you sail towards America, very often they were afraid that you would fall off the edge of the Earth. And after that, there are dragons and beasties and all kinds of nasty things. So this is exactly like that. We don't know what happens when you get to a certain point distance from the singularity. That's the end of physics. It's the edge of space-time. Okay, let's get away from this depressing topic. But let me just mention that the object at the center of the black hole, and I'll mostly talk about non-rotating black holes, that object is called a singularity. That's a mathematical term which basically means that says we don't know what's going on there. It's a place where the curvature is very, very large. Okay? And the word singular is used to say is one of a kind. That's the only meaning that you can attach to this sound. For example, a most singular phenomenon. Now, I'm going to show you another demo, which is, yeah. now take a look at this wheel. We should maximize it. Okay, what I've got here is a wheel, and inside all these red circles are atoms in their excited state. I already told you that atoms can be in an excited state, and they can be in a ground state. The excited state atoms have more energy, and therefore they weigh more. The unexcited atoms here weigh less than the excited atoms, so this thing would tend to rotate in this direction because there's more weight on the left than on the right. At some point, all the excited atoms will come below, and the motion would stop. But I'm smarter than that. What I will do is, as the excited atom passes through the bottom of this picture, I will send the light up with a fiber optic tube and excite the atoms at the top, so that the left side is always excited, the right side is always de-excited. And this is what happens. You get a wheel that keeps on turning forever. We can use that to make energy. We can power our cities with it. There has to be a flaw in this. This is the perpetual motion machine, something which is not allowed by physics. And the flaw is simply that I'm assuming that the light emitted from this atom here can be used to excite the atom here. The truth is that that does not happen. The light emitted from here gets redshifted here. So just like you have a Doppler shift, when you have sources and observers in motion, in relative motion, you have a gravitational redshift when a light tries to go from a lower point to a higher point. At the higher point, you see a smaller frequency. So if, for example, we had an orchestra where in a strong gravitational field, and one section of the orchestra was playing down here, and the other section was playing up here, the guys down below would have to play at a certain speed. These guys can play much slower. You won't find them moving as fast. I mean, you need better musicians to be down there, the ones who can play faster to be down there. So there's a stretching of time as you go from the lower places in the gravitational field to the higher places. I told you that atoms have spectral lines, and they have frequencies, preferred frequencies, and the best clocks in nature are atomic clocks. So this also means that clocks run slower in a gravitational field than they do higher up in the gravitational field. So if I go to outer space, the clock will run at a certain rate, but if I come down to the Earth, that clock is going to slow down. This is called the gravitational redshift. It's one of the predictions that comes from the general body of ideas of relativity. So is this clear? There's going to be a gravitational redshift. Oh, no. It is proposed a long time ago. Yeah, I'm sorry. Yeah? Yeah. No, it was, just a minute, I'll answer this question. The question is whether this is seen or not. The answer is it's very much seen. The latest experiment is that two aluminum atoms, 30 centimeters in height from each other, have a different frequency. One has such good clocks these days that one can say that this atom is running slower than this one as a clock. Aluminum clocks have been measured with a 30 centimeter height difference. It's a tabletop experiment. Of course, when you talk about the GPS, there are much bigger effects which have to be corrected for routinely. The redshift is a fact of life. And in fact, it affects the military, because when they want to use a GPS, they have to actually put in relativistic corrections. Yeah? Okay, there was a question there? Yeah.
Basically, even if it's a redshifted light travel,
yeah,
we don't generally lose the entire energy, right? So
no,
even
see that if the light is redshifted, the energy is reduced. You have to supply it some energy. For example, you could put a pinwheel there to hit the photons and give it some energy to increase the frequency by the Doppler effect. And then you can excite the atom there, then you can make this engine go. But it's an engine in which you're putting in as much energy as you're getting out. So it's not a very useful engine. I mean, it's not a perpetual motion engine. Okay, another effect is that if you have a person who's living at the ground floor of a building, he grows, if you compare him with somebody who's at the top floor, you can have something like a twin paradox, that two twins, one of whom who lives higher up, will age faster than the one who lives lower down. That's the twin paradox in a gravitational field. I think I don't have time to explain this a little bit, but maybe I can show it. Yeah. this is the vertical direction. This is higher, and this is lower. And an atom from here is sending signals at the speed of light over there. So what is surprising is that, well, this is the atom staying at a fixed location, and this is time. What you're finding is that this distance here, which is the time spent, this time between two signals sent from this atom, is longer. I mean, this length here, suppose this length was 1.1 second. This will be 1.0001 seconds. I'm assuming a strong gravitational field. This is the kind of effect that you will see. We'll return to this point later. I don't know what happened. Okay. Now, there are some common misconceptions in the general public among black holes. But before I do that, sorry, I should show you the video. So I told you that I was going to make use of the analogy between light and sound in order to explain what a black hole was. There's an acoustic analogy for a black hole. So I'm going to call that an acoustic black hole. So this is an idea that was put forward by Andrew, who's a Canadian physicist. And the idea is to replace the speed of light with the speed of sound, so that the black holes, which are normally very exotic objects, can be brought into laboratories. So I'm going to show you a video from a laboratory where this experiment is being done. The experiment is being done in Nottingham, which is the place where Robin Hood was, no? The University of Nottingham. And the name of the scientist who's doing this experiment is Silke Weinfurtner. What I'll do is to just show you a little bit of the clip, because I don't have time to show you the whole thing.
So we are in the black hole laboratory. What you're looking at, that's an analog rotating black hole. As a first step, we fill up the space in here in the back. We put water in there, and then we also put what's called fluorescent dye. Makes your fingers dirty. It's actually sort of orangey, but then it takes the blue part of the spectrum of the light and converts blue into green. There are about 2,000 liters of water in there. If you follow me, here we have two valves which we can open and control how much is going through each inlet. We have two inlets in our tank. We feed in the water from this side and also from the other side. And so we have this rectangular tank, and we fill in the water this way. So by feeding it in this particular way, you give it angular momentum. And then what we have a hole in the center. These are exchangeable center holes. The water is coming in, and because of the way we feed it, it starts spinning, and it's draining in the center. So it's a stationary draining fluid flow, or just a bathtub vortex flow. So this is not a black hole for me or you. That's a black hole for small excitations in this system. So if you look at sound waves or little ripples on the surface, this is what we are interested, they have a certain propagation speed. And if you set up fluid flows where the background velocity of the flow exceeds the propagation speed of the little ripples, you can set up what's called analog horizons. So suppose you're in a one-dimensional fluid flow.
Yeah, that's basically it. I mean, I don't want to show you the whole video, but you can look it up on the internet. The idea is that you're doing an experiment which is the analog of a black hole out there. The velocity of the fluid is something like the gravitational field, and the ripples on the fluid are like the speed of the ripples is the speed of light. So this is an acoustic black hole, and as I said earlier, this uses the sound light analogy to bring the whole discussion into the laboratory, where it's not practical to actually make a real black hole. Okay, there's some common misconceptions about black holes. One is that people think that black holes have a special kind of gravity which sucks material from the outside. There's no difference between the gravity of a black hole and the gravity of any other object. If you make the Earth into a black hole by compressing it to 1 centimeter, the moon would go around the Earth just as it does now. There's no real difference between gravity from a black hole and from ordinary matter. Another misconception is people think that they have to be very dense and massive. Neither of these is true. Black holes can be as dense as light as air if they are big enough. What really matters is the ratio of the mass to the radius. Here's a picture of a black hole. And there's an effect which I didn't talk about. See, this is an accretion disk going around the black hole. And what you're seeing here is a picture of the disk which is behind. The light that's going up from there is bent and comes to our eyes here. And this is a picture from the movie Interstellar. And similarly, you see the same disk where light has been bent under the black hole. Another picture is over here. Here you can see another effect which I've also not described. Accretion disk is going around here. This is, of course, the disk on the other side. But the disk here looks much brighter because the particles are the matter is moving towards you at something like half the speed of light. So this looks much brighter than that because it's going away from you. Okay, maybe I'll pause here and start on my next topic, which is steam engines. Yeah. Yeah, the Doppler shift will make all the energies go up. That's true, that's one effect. But it also directs all the photons towards you. That's a beaming effect. There are two effects which are there. So it looks much brighter. Okay, now I'd like to start this with a question which I heard from a little girl who came to our institute from Kerala. So she must have been about 11 or 12 years old. And her question was that in the biology class, we are taught about environment. And we're told that we should conserve energy. Right? And in the physics class, we're told that energy is conserved. So her question was, why should we bother to conserve energy if energy is anyway conserved? It's a very good question. And actually, what is good about the question is that completely internally generated. She was genuinely puzzled by this. So does someone have an answer to offer? Yeah. Yeah. Okay. Yeah. Let's. That's right.
That's right. But when we say that we should conserve energy, that means we should conserve energy in the form that we can use of.
Yeah. So there's a notion of useful and useless energy. Yeah. Right. Yeah. So all forms of energy are useless. You can freely convert energy from one form to the other. In a hydroelectric dam, you have gravitational potential energy converted into kinetic energy of water, which is converted by a turbine into electrical energy. Right? All these energies are freely interconvertible. But there is
not 100% interconvertible. There's some loss
at every stage. And that loss is heat. The only really bad source of kind of energy is heat. Heat is a degraded form of energy. And all the other forms, in principle, can be converted with very high efficiency. But heat, you cannot, if you waste energy in the form of heat, you cannot get it back into normal energy. Yeah. So let me explain that a little bit more. When we talked about the steam engine, I said it converts heat into directed motion. So what is heat? It's basically the same energy which has been put into many different directions. So undirected motion is heat. Molecular motion is heat. And directed motion is real energy. If I take this knife and I drop it on this table, so if it falls down there, that energy all goes into heat. It's the molecular motion of the table. There's no process known by which the molecular motion of the table can kick the knife back up to the height that it was. That is the second law, and it basically consists of two parts. The first law of thermodynamics says that energy is conserved. The second law says that you cannot completely convert heat to work. The limitations of converting heat into the work are basically the principles of thermodynamics, and it tells you that heat cannot be, once you wasted energy, you cannot unwaste it, which is true even for money. Once you've bought a useless thing in your house, nobody's going to buy that thing off you and give you back your money. Yeah. Sorry, no, even with sound, in principle, you can get back that energy. Heat is not as, sound is a better form of energy than heat. Yeah? So heat is the worst form of energy. That's the model of this part of the story. So I need some people to distribute these envelopes. So some volunteers, yeah, I give it to him. Yeah. So I want you to form groups of 5. Don't open the envelopes yet. It contains some toxic material. We'll get to that later. So if the second law of thermodynamics was not there, it would be completely consistent with the first law for us to have a fridge which cools itself automatically, and we can use the energy, the heat energy from the fridge to light up the house. So we wouldn't have to pay any electricity bills. Yeah? So that we're not as lucky as that. We're constrained both by the first law of energy, which says that the energy is conserved, and the second law, which talks about a different quantity called the entropy. The entropy is a measure of disorder, and the second law is basically telling us that disorder of the universe always increases. So if you have a closed system, for example, I take a gas and I put in some matter, if I wait long enough, that matter will attain thermal equilibrium. That is to say, it will all be at the same temperature, and then I cannot extract energy from it. So closed systems have a fixed total amount of energy, and this energy will tend to dissipate into heat. That's the way everything goes. Friction causes heat, and that's how you lose energy. The final state will maximize entropy for a given energy, and this is called a thermal state. It has a certain temperature. We cannot extract work from something, from a body which is at a fixed temperature. But we can extract work from two thermal systems at different temperatures. So I will just show you another heat engine, which is not made from steam, but which is made from rubber. So this is a gizmo which one can actually make, you know. And if you make it, it'll work. See, what I have here is a bicycle wheel with a heavy hoop at the side here. And these are all rubber bands. Now, rubber is a very interesting material. Rubber consists of a lot of long polymers, like this. If I take rubber and I stretch it, it has all the molecules have to line up like this. They're very ordered. If I don't stretch it, they're disordered. They can be in any configuration. So if I have a polymer and I heat it like this, it tends to go into, it tends to go into nonlinear configurations. That is, configurations which are not in a straight line. And there are a lot of those configurations, so the ends come together, and rubber contracts when it's heated. It's unlike most metals which expand when they're heated. So polymers have the property that because of entropy, they like to stay together. And the whole subject of soft matter studies polymers like DNA and the cells in your body. Okay, so this is a state of very high order, and this is a state of disorder. So when I heat rubber, it's going to compress on this side, and let's suppose that I heat this side. What will happen is that this side will compress, and the hoop will move slightly to the left. So before I've done anything, the hoop is perfectly symmetrical, let's say, and the center of mass was exactly going through the axle. Now, what I will do next is to put the two sides. I don't know what happened there. Okay, the two sides of this thing are in different temperatures. So the hoop is moved to the left, and it comes down like this. When it comes down, the cooler rubber tubes come here, and then they contract, and this thing keeps on rotating. This is a heat engine that will actually work if, yeah, sorry, I've done something. Yeah, this is the one I wanted to show. Okay, for some reason the colors are not coming out, but this is a machine that works because the right side is hot and the left side is cold. Do you figure out how it works? Yeah, what will happen is that when the rubber compresses, the hoop will move to the left a little bit because it's hotter there, and the center of mass of the hoop will be over here, and it'll come down. As it comes down, the rubber will move, the rubber will move from the colder place to the hotter place, and those rubbers will now contract. So it's always bigger rubber bands on this side and smaller rubber bands on this side. So this will actually generate energy, generate directed motion, and it's coming from heat. The heat came because there was a temperature difference between the left and the right side. And if you keep on running this machine, that temperature difference will be evened out, because when the cold rubber goes from here to there, it will go there and remove energy from the hot place and take it to the cold place. So this will actually work, and you know, I encourage you to try to construct this machine by using nothing more than rubber bands and a wheel. Okay, now the relation between disorder and heat may not be entirely clear to you. Oh, I'm out of time. It's okay. The relation between heat and disorder may not be entirely clear to you, so let me just say a few things about that. So if you open your envelope, you'll find rubber bands in there. So just distribute to your neighbor and give everybody a rubber band. Ignore the piece of paper. Just take the rubber bands out and give it to them. So if you take a rubber band and you put it on your forehead like this, and you pull it tight, you'll find that a little bit of heat comes out into your forehead. Because when you pulled it tight, there was some disorder which got thrown out of the rubber band, and that heat came into your forehead. And when you release the rubber band, the reverse happens, and you'll feel cool on your forehead. Like that. You feel it? Yeah? Yeah. It's a very simple demonstration of the fact that entropy is somehow connected to heat. Okay, I think I'll skip the relativity bit because I've sort of run out of time. So I just mentioned earlier that space-time is going to be curved in the presence of gravitation. And an argument for that comes from the redshift. If I look at this picture, what I've drawn here is a parallelogram. A parallelogram has got sides which, by the way, when we have the speed of light, which is universal, we convert all times into distances or distances into times. So we don't need to distinguish between space and time. So there's a line here of a certain length, and these two are parallel lines. And I would imagine that this forms a parallelogram. But in flat space, the opposite sides of a parallelogram have the same size, have the same length. But here, because of the redshift, here's a parallelogram where this side is shorter than the other side, even though these lines are parallel. So that proves that in gravity, space-time would be curved. So in order to demonstrate the curvature of space-time, which is a little difficult, I've in fact made it simpler by talking about the curvature of space. If you open the envelope, you will find two pieces of paper. First, take the one which is 3/4 full. You'll find a point marked P on it and 2 points marked O. Bring them together. And you will see a triangle. Yeah? Has everyone got these sheets, or somebody in the neighborhood has the sheets? Yeah, you get a triangle, and you notice that the sum of the angles of the triangle is more than 180 degrees. So this is a case where you have a curvature only at the cone, but I'm not drawing any lines through the cone. I'm drawing lines only in the region where I know what's happening. And I find that the sum of the angles of a triangle is more than 180. Now if you take, everyone got that? Okay, now you take the other sheet of paper, and then that's a full sheet. You just fold it in half around the point P. And then you'll find there's a figure which I would like to call a biangle. A triangle has got 3 angles. This has got just 2 angles. A and B are 2 points connected by 2 straight lines, and it encloses some area. This can also happen in curved space. So this, what it means is that in relativity, you can have 2 light rays which depart from each other and come back and refocus. So 2 straight lines, in flat space, 2 straight lines can cut each other only once. But in curved space, you have 2 straight lines cutting each other twice. So strange things happen when you have curvature. And that's exactly what we study in this subject. Okay, I think I'm badly out of time, but the point of this lecture was to get to Hawking's work. So the first thing is that I told you about the singularity. what Hawking proved is that singularities are generic. That is, under a wide range of conditions, you will have gravity dominating over all other forces and ending up in a singularity, a place where the theory breaks down. Now, this is a remarkable theory because it's able to predict its own demise. It tells you when it's going to fail. And it's telling us that there's new physics to be discovered beyond general relativity. And in fact, a lot of the work all over the world is going on in this precise area. Gravity will lead to extremely large curvatures, and the laws of physics will break down. And it's telling us that there's new physics beyond general relativity. And a lot of this work was done because, was made possible because of some work done in Calcutta by Amal Raichaudhuri, who proved that if you have matter moving, it will always tend to attract itself. The attractive nature of gravity was put into mathematical language by Raichaudhuri, and that's what results in the singularity theorems. Both light and matter focus with gravity. Now, Hawking proved, using the Raichaudhuri equation again, that the areas of black holes always keep increasing. Now, that is something slightly counterintuitive, but it was true. He was able to prove this mathematically. For example, if you have two black holes merging, the total area is always more than the areas of the two black holes. And you cannot have a black hole splitting into two black holes. Like you can have cells splitting into two, but you cannot have black holes doing the same thing. Now, this led to a suggestion by Jacob Bekenstein. He suggested that the area is like entropy. In other words, that there is something in a black hole which is like disorder. And this suggestion was dismissed by everybody, including Hawking. And it's easy to understand why it was dismissed. Just because area increases and entropy increases, there's no reason to think that the two are the same. For example, I know that the universe is expanding. I also know that my waistline is expanding. I cannot immediately conclude that my waistline is the universe. Right? Yeah. But if you look at the laws of physics, there are very few inequalities in physical laws. Most of them are equalities. Entropy increase is the only one law that I know which talks about a law as an inequality. So if you discover another law, which is also an inequality, perhaps the two might be related. There are not so many of them around. And finally, the brilliant work that Hawking did was, okay, first I have to explain why even Hawking did not believe it. The reason he did not believe it, apart from the reason I gave, is that if black holes have an entropy, they would also have a temperature. And if they have a temperature, they would radiate. But we know that black holes are black and they do not radiate. So that's the paradox, which was resolved by a calculation that Hawking did. He was able to show that black holes actually radiate, and that radiation is called Hawking. They would have, if they have an entropy, they would also have a temperature, and they would radiate. And that was shown by Hawking. So I've said all this a little bit before. We can use, if it was not true that black holes radiate, we can use black holes to violate the second law. So the only way out of this is to ascribe entropy to the black hole. The reason you can violate the second law is that you can take some entropy which you've generated. For example, all the garbage that comes out of your kitchen, you can put it into a box and lower it into a black hole and not only extract the energy from it, but also reduce the entropy of the universe by throwing away the entropy which you have in your kitchen. You could take all the plastic in the universe and put it into a black hole and extract the energy. Now, that would violate the second law unless the black holes also have a temperature and an entropy, and that's exactly what Hawking showed. So this led to deep connections between gravitation and thermodynamics, and it's a subject of current research. And let me just say that black holes are macroscopic objects with a microscopic description. So many things which we normally talk about in macroscopic physics, we can talk about from a fundamental point of view. Now, current research, which has been motivated by Hawking's discovery, is one of them is the question, is information lost in black holes? In other words, if you kill somebody and throw the body into a black hole, can the detectives look at the radiation that comes out of the black hole and discover your crime? That's a very hard question, and many people are working on it. This is called the information paradox. There is general conflict between gravity and quantum theory, which people are trying to resolve. One of the questions is, where are the degrees of freedom that represent black hole entropy? Are they stuck at the boundary of the black hole at the event horizon? Definitely there's new physics beyond GR, we know that, but what is that new physics? Is it quantum gravity, some kind of unified field theory or string theory? So let me just end by saying that physics and science in general has got two components, one of which is imagination, and the other is skepticism. And both are needed for progress. So while the imaginative ideas have to be put forward, but they have to be put forward in order to be tested. And finally, you extract the truth from these imaginative conjectures. What survives is the body of physics that we know. Thank you for your attention, and sorry for going over time.
Thank you, Sam, for a wonderful lecture and demonstrations, and most importantly, not killing any of us here.
Yet. Not killed anybody yet.
Yes, yet. So be ready. So we take questions. There are 2 mics at the edges. So if you're close to, just go there. If not, put your hand up. And I see several hands. There's one here.
Every matter in the universe tried to go to a lower energy form.
Yeah.
Why does the entropy increase then?
Yeah, it does. For example, if I take, why does the entropy increase?
Every matter tries to go to equilibrium.
That's right.
So entropy is opposite of equilibrium. Why is it increasing?
Entropy is actually the same as equilibrium. Every system tries to go towards maximizing entropy. Well, I don't know, it's the second law of thermodynamics. I guess I don't understand the question. Let's take a concrete example, okay? I'll take some matter in a box. And if I were to just minimize its energy, all the matter will go to the lowest part of the box because the potential energy is least over there. Right? But if I look at gas in a box, it's not at the bottom, it's distributed all over because it likes to have more disorder. Yeah? So that's the competition between lowering energy and maximizing entropy. So the physicists put it in a different way that we minimize a different quantity, which is called the free energy. The useful energy is minimized. But you cannot extract more energy than the free energy from any system. I'm not sure I answered your question, but maybe, yeah, okay.
There's a question.
How do you detect the radiation that's coming off the black hole? Has it been detected? Has it been observed?
Yeah, it has not been detected. The reason it's not been detected is that there are some fundamental constants which are very uncooperative. The speed of light is very large. The gravitational constant is very small. All of this conspires to make the temperature of a black hole extremely small. For example, if you have a solar mass black hole, the temperature would be something like nanokelvin. It's a very small temperature. Okay? But there's always hope. When you look at the acoustic analogy, the speed of sound is much less than the speed of light. You can bring these things into the laboratory. There are people in Israel who do experiments with acoustic black holes with quantum fluids. So they have superfluids which are being forced to go through the same kind of thing which I showed you. And they, in fact, think that they have discovered Hawking radiation, but it's disputed. So one of these days, we might actually see that somebody claims and successfully claims that they've detected Hawking radiation. So the imagination part is there, but the skepticism is also there. So not everybody believes the demonstration.
Hi, Joseph. It's me again. I'd like you to address 2 points that I have, followed by a question. The first thing is I want you to tell me about the virtual particles at the black hole and how the study of the entropy actually gives insight into the study of the virtual particles popping in and out of existence. That's one thing. And the second thing is I want also you to address about whether the black holes are really black or not. That's the second one. And earlier this Jan, I had the privilege of meeting Kip Thorne at the lecture at ICTS, and I sort of framed a similar question which I'm about to tell you right now. And the question is this: as an advocate of science, how do you approach people who would deny the existence of evidence in the actual sense and who nevertheless go ahead with the misconceptions, whatever they hold so far? It's because you can usually define gravity to most of the people who are educated enough in a way goes like this. It's a 4-dimensional construct of metric tensor imposed in a Minkowski space of a geodesic or something, or probably something like, you just take a step over the building and see how it works. There are 2 versions of it. And then, what's your take on it? That's because we smart people who are at a very small gathering talk about so many big things sitting in this room, but outside you see people who are in the positions of really good power and all that, who are absolutely idiotic.
I think I'd like to stick more with the the science, and less with the sociology. But let me just say that not everybody here is rational. I don't think I'm completely rational either, I mean, we're all irrational beings. We try to be rational, but we don't always succeed. And let's not try to convert people. Let's at least understand what we do understand, no?
I do get it. I want your take on it in specific.
No, my take is that I'm not particularly rational either.
All right.
Yeah.
Okay.
Yeah.
So you said that when you go inside a black hole feet first, you get stretched all the way and squashed from here.
Yeah.
So I've read it somewhere that it's true that when you get into a smaller black hole, the intensity of stretching and squashing is more, and in a bigger black hole, the intensity of stretching and squashing is less.
That's absolutely right. You guys know far more than your age suggests. You're absolutely right about this. Small black holes have a higher tidal force. How did you learn all this? Yeah, you're absolutely right. And in order to appreciate it, you have to, write some equations, which you will do shortly when you get out of school, I'm sure. Yeah.
We do have a smart audience. So this is the question there.
Good evening, sir. Have a doubt. You said that the black hole's area will increase.
Yes.
But then according to Hawking's radiation, mass will be ejected out, and then that mass will have a kinetic energy, and that kinetic energy will be given out from the black hole by its mass.
Yes, that's correct.
That is, black hole will slowly, but surely it will lose its mass and will shrink.
Yes, right.
So
No,
how will
right.
the area of the black hole increase if it shrinks and,
You're right.
if, it's,
You're right.
and if it loses mass?
Yeah. So before Hawking radiation was discovered, the area theorem suggested that black holes will always increase their area. Yeah. So after the discovery of Hawking radiation, it was argued just as you did now, that they will be putting out energy, therefore they will lose mass and they will shrink. So the black hole area expansion was only claimed in the absence of Hawking radiation. In the presence of Hawking radiation, it will actually shrink. And that's a quantum effect. Classically, it will only increase, but because of quantum mechanics, some little bit of energy will leak out of the black hole, and that's what Hawking radiation is. But the process of losing area is extremely slow for solar mass black holes, and is extremely high for tiny black holes, which are, like the size of a mountain or something like that.
So how long will it take?
I'm sorry? Yeah, the total entropy of the universe will also always increase. The area will decrease, and there will be radiation put out. The total entropy will increase, consistent with the second law.
Okay, I had one more doubt then. Is the universe expanding in all directions?
Yeah.
Or does it have some kind of, like in unidirectional? That is, does it have a preference that it has to, expand in a particular direction?
Okay, the universal expansion is isotropic. That is to say, there's no direction singled out. So what we mean when we say that the universe is expanding is that every point is moving away from every other point. Yeah? So more space is being created between the galaxies. And you started out by saying, I have a doubt. It's a good thing to have doubts. There's a very famous guy called Francis Bacon. He said, if you start any inquiry with certainties, you will end with doubts. If you start with doubts, you will end with certainties. Okay.
Can we use black hole theory for our day-to-day applications? Or where can we visualize the application?
Yeah. No, so actually, that's also a slightly sociological question, but I'll answer it briefly. Nobody knows what applications will come out of what science. Okay? Gauss prided himself on the fact that number theory had no application whatever. Years later, all of cryptography and the science of secret communication depends on Gauss's work, which was done at a time when he believed that it would never be applied. Yeah? So none of the mathematics that you see here will immediately have an application, but science as a whole does have numerous applications. And if you want to talk about it from the point of view of tax dollars or tax rupees, as society has got back far more from science than it has put into it. Of course, what we want from society is support for scientific research, freedom to think freely without fear of favor, and also occasional resources of people coming in from the general society into the scientific community and contributing to our knowledge. Yeah? So knowledge is a very good investment. If you ask any middle-class family, they will put aside money which is meant for milk and educate their children. Society should do the same thing. Sorry. Yeah.
Hello. Here. So earlier on you mentioned very briefly the difference between heat and normal kinetic energy, right? So you said something that heat is disordered kinetic energy.
Yeah.
How would you actually differentiate,
how to differentiate it? That's a very hard question because it depends on the scale at which you're looking at things. For example, if you look at wind, you might say that the wind is disordered, but if you put up a windmill, you can extract energy from the wind. So the question is whether you can extract that energy and convert it into something useful or not. If you cannot extract the energy, you call it heat. If you can, you call it kinetic energy. But heat is also kinetic energy, but in such a disordered form that you cannot really access it.
Okay, so on like the bottommost level, does that mean that can't you extract energy from any disordered molecules? So technically speaking, there is...
No, you cannot extract energy from anything which is completely random and unpredictable. Just as you cannot predict the stock market, there are certain known factors which you can predict. But after that, what is left over, if it's completely random, you cannot really get any benefit from it.
Okay. Yeah. And one more thing.
Can I restrict to one question? There are two minutes. We can come back. Yeah. There's a lady behind the pillar. Here.
Hello, sir.
Yeah.
Here, Sam.
Okay, so...
I think we're playing hide and seek here. Okay.
So, sir, when I saw the movie Interstellar, I never really understood how the daughter became older than the father, and I asked many people. So I'm guessing that is the twin paradox. So
Exactly.
Could you explain that a little?
Exactly. So the father goes into a place where the gravitational field is stronger, and years later he meets his daughter at her deathbed. So he's still relatively young, and she's old and dying. And the fact that the two people have different ages is not that paradoxical. Actually, let me explain this using distance rather than time. If you want to go from here to Indiranagar, you can take one route that goes through MG Road. That will cover a certain amount of distance. If you take a different route, it will take a different amount of distance. So the distance between 2 points depends on the path which you followed. Same way in relativity, we talk about space-time. The distance between two space-time events depends on the whirl line that you follow between them. And the two followed different whirl lines, and therefore their ages were different. So this is a very old thing called the twin paradox. It's not a paradox at all, actually. So it's a good thing to understand what a paradox is. A paradox is a truth that's standing on your head, on its head, in order to attract attention, right? So similarly, the information paradox, I'm sure, will be resolved to the same level of, of felicity shortly.
So we have two long
By the way, I would appreciate more questions from girls, because I notice it's only the guys who ask questions. Science is gender neutral, right? And yeah.
Anyway, so until so is a question.
So basically, it's more of a confusion I have. We have always been told that light travels at 300,000 kilometers per second, but no one has actually given reason why does it? Why does light travel at the speed it does?
Your guess is as good as mine. There's no fundamental reason why light travels at its speed. It's one of those things which I don't think there's a good answer to. If anybody has an answer, well, I don't have an answer to that. Why it is this and nothing else. In fact, for me, the speed of light have been put equal to 1, because I use it to convert time into space. And after that, I never bother about the speed of light. I don't, yeah.
There's a question from online, so several people are watching.
Okay.
There's one from Anshuman Upadhyay, and the question is, how do black hole event horizons grow in size? You talked about the area, but what about the event horizons?
Actually, the event horizon is a very strange object. It's only determined in the infinite future when you trace back light from the future and see where it ends. So you might think that the event horizon is here, but if some extra matter falls in, you'll find that it actually jumps to another place. But you'll never find out about all this till the end of time. Yeah? So it's got what we call a teleological significance. It's a relatively advanced question. I think I should stop here and not really. Yeah.
Just one quick question.
Yeah, sorry. I think there's a question here from, yeah?
Like everything just came out suddenly. So these black holes are trying to take us back to that state of Big Bang, like point of singularity? Because they're compressing everything, right?
That's right. There was singularity in the beginning, and there are also singularities in the end. Life seems to be full of singularities.
Okay.
Yeah. So I didn't understand.
So these black holes which are there in the universe, will they take us back to that state in which we came from initially? Like at the time of Big Bang?
Actually, I don't know. One of the discoveries from astronomy is that the universe is accelerating. So it's going to get colder and colder and not hotter and hotter. Right? Yeah. So my answer briefly is no. And I'm sorry I was rude to Rukmini, because I saw, one of my scientific colleagues, I can afford to be rude to her.
So I just wanted to ask you, can you summarize a little bit why this analogy between steam engine and black hole? It wasn't clear to me.
Yeah. So I can think of a black hole also as a thermodynamic object having a temperature, yeah? And I can think of engines which run using the temperature difference between a black hole and some other thermal object. So I showed you one example of an engine running between a hot and a cold temperature that was using rubber. But I can make one of those heat sinks the black hole. For example, I can take entropy and reject it into a black hole, which is at a very low temperature, and run a heat engine like that.
One from this.
Yeah, I'm sorry, I think I prepared too much material. I sort of overestimated the time. That's why some of it might have seemed disjointed.
Hi, as you mentioned, Hawking radiation was a product of Bekenstein and what do you call, when the black hole merge, the area will grow.
Increase, yes.
Yeah, increase. In terms of particle physics perspective, like at the same time, Dirac came with this particle antiparticle analogy, right? So why the people think in that perspective also, like virtual particles, the quantum fluctuation will happen at the event horizon.
Yes, yes.
So I'm just curious about the history part of that. Like, it came from that perspective, or it came from the other?
No, it came from the picture of particles and antiparticles was given after the derivation. The derivation that Hawking initially gave is completely mathematical. And then he was trying to explain it in simple terms, and he gave the idea that maybe there are entangled pairs of particles produced at the horizon. One falls in, one comes out, and that's the source of Hawking radiation. There's some physics in that picture, but the mathematics came first because the result was so strikingly spectacular that he wanted to be sure of his mathematics. And I should also say that I'm slightly oversimplifying. Hawking was not the only one around here. There were other people like Starobinsky and Zeldovich and Parker who were very close to this picture.
Okay.
Hawking just made that extra jump.
Okay, one more question. So you showed that experiment where there's water is going and this, yeah. So why not the simulation instead of these experiments?
Why not the?
Simulations, like.
Yeah, you can do a simulation. That's true. You can do a simulation, yeah. You can do that also, yeah.
Okay, so what?
Okay. Let's just, there's a long queue. There's people there.
So my question is about the signature frequencies emitted by the elements. So we have studied all the elements on Earth and come to a conclusion that a particular element emits light in a particular frequency or combination of frequencies.
Right.
But the bodies in the universe, they just keep floating around different speeds, and they probably, when they emit light, the light will be red shifted or violet shifted.
Right.
So how do we know that that is the same element that we have here?
Yeah. So what the effect you're talking about is that there could be thermal motion of the atoms.
Yeah.
And that will Doppler shift things.
Yeah, even the bodies will be moving around in a particular velocity.
That's right. So typically those velocities are small compared with the speed of light.
Okay.
And what it does is to just broaden the spectral line. You can still recognize the spectrum even though it's been broadened.
Oh, okay.
Yeah. But when those motions are very large, as happens for the Hubble shift, the whole spectrum will be shifted by a constant factor, and that's how you detect the cosmological redshift.
Okay.
So Hubble was able to say that, for example, some element in a distant galaxy, for example, calcium or something like that, the spectrum was the same as the calcium that we have on the lab, except that the whole thing is shifted.
Oh,
yeah?
okay.
So initially it was not recognized because they were looking to see calcium lines here. There was nothing there. They had to go quite a distance before they saw the calcium line.
So there's a pattern, anyway.
There is a what?
There's a pattern. I mean,
yeah, there's a pattern, yes.
And last question. So do we know anything about the formation of supermassive black holes in the center of the galaxies? We know that the other regular black holes...
Our black hole has got a supermassive black hole in the middle.
Yeah. So is there any idea about how it is formed?
Well, it's over a period of time, stars form black holes and keep accreting other stuff. It's formed over millions of years. No?
Okay.
I'm not particularly well informed about this topic, but that's how I imagine.
Right.
Yes.
Thank you.
Can I restrict? Please restrict to one question. We can come back later on.
Yeah. So continuing what he just said, so we know that there's a supermassive black hole at the center of our galaxy. So what's going to be the end of the black hole? Like, does it live on? Like, stars fade away? What's going to happen to a black hole at the? Is there an end?
If you stop feeding matter into the black hole, at some point it will come. Let's do the same experiment that we do with the gas. We don't disturb it in any way. We don't supply matter. So it will settle down into some massive object. It will have a gravity. There's nothing around it. and it'll start Hawking radiation. But it'll take a long time before it completely radiates away. Either it will completely radiate away, and here's where our knowledge is not very sure, or it could end up as a remnant, which has got a mass of 10 to the minus 5 grams. It's a very small remnant. It's a Planck-sized remnant. That's also a possibility. Yeah? So
Also,
one of the two things will happen.
If there are no objects around a black hole, it would be difficult to identify it, right, without the accretion
Yeah,
disk.
that's a very good question. It's also a very common question. See, you cannot see a black hole because it's black, right? In order to see something, it must emit light. So for example, if I turn out all the lights here, I won't be able to see any of you, right? With no light. But if I shine a torch at you, I can see the scattered light, and that's how I see you. That's what's happening now. If I do the same thing with a black hole, suppose I have a black hole there, and I shine a torch directly at the black hole, and the rays of light from a torch spread out like this. Some will go around the black hole, all the way, be bent around, come back to my eye. And the net picture is that I'll see a black hole which is really black in the middle and have concentric rings of light. So you can see something. Or if the black hole has a companion, you'll find that it's doing a dance with a companion, and the dancer has an invisible partner. So that's another way to see a black hole. Another way also is that you see it from the accretion disk, which is also matter outside the hole.
Thank you, sir.
There's a question.
Sir, does
Yeah. Sorry, very important point. You can also see it from gravitational waves. It's not just light, but you can also see the gravitational waves that are emitted by black holes, as has been done recently. Yeah, where am I looking next?
Sir, does time stop at singularity at the center of the black hole?
Actually, it stops earlier than that. It stops at the event horizon, in the sense that if you give somebody a watch and push him into a black hole, you look at his clock to see what time it reads. At the event horizon, you'll find that it stops. His clock stops, and you don't see him progressing beyond that. Yeah. So the passage of time also depends on who you are, as we saw with the other question about the twin paradox. Yeah? So in a sense, you can say that the person never crosses, but you'll only get a finite number of photons from him before he goes black completely.
Then how does the black hole evaporate?
The black hole evaporates through a quantum mechanical process by which particles are emitted. They tunnel out of the black hole. In fact, tunneling is a purely quantum mechanical phenomenon, which is not there in classical theory. So if you have a mountain here, and you have a quantum mechanical particle here, it doesn't have, classically it would have to go over the mountain. You must give it enough energy. But quantum mechanically, it can go through the mountain and appear over here. This process is important to all of us. In fact, we all depend on it for our lives. Because in the sun, the temperature of the center of the sun is only about 10 million degrees. It's not hot enough to start nuclear reactions. But nuclei have a Coulomb repulsion barrier, and they can get through the Coulomb repulsion using quantum mechanical tunneling. It's because of tunneling that the sun shines. So remember that. If anybody asks you what is the use of quantum mechanics, tell them that the sun shines because of quantum mechanics.
Sir, another question. You gave that example of that.
No. We can come back. The last, it goes into a discussion then.
Yeah.
So last three
I
questions.
think
So one from there and
MC,
one
tell him, yeah?
from there. Go ahead. You have one? Okay, fine. You go ahead.
My question is about Hawking's radiation again. See, Hawking's radiation, being a radiation, it travels at the speed of light. So now, obviously, it can't originate from inside the black hole because light can't escape from it, because the escape velocity of the black hole is the speed of light itself. So now, is Hawking's radiation going to arise from the event horizon, or from where does it arise?
Yeah, okay. Those are all very good questions, but let me just start with the first one. The first one is that it's Hawking radiation is light. Yeah? Actually, Hawking radiation is thermal radiation, and thermal radiation includes all kinds of particles, including light.
Yeah, I know that. I'm like, radiation is going to travel at the speed of light, right?
No, when I say thermal radiation, I'm using the term more generally than you are. So Hawking radiation is a kind of radiation which I'll call thermal radiation, which includes light. Also, it includes particles. Every particle will appear in Hawking radiation with a probability that's given by something like the Boltzmann factor. Higher energies appear less. So electrons will be much fewer, but there will be electrons in Hawking radiation. In fact, every kind of particle in the universe will be coming out in Hawking radiation if you wait long enough. And if you really wait long enough, you can get the complete works of Shakespeare bound in leather coming out of a black hole, because there's a finite probability for that to happen. So it's not always light, it's matter as well as light. The second question is how does it come out of the black hole, it can come out through quantum mechanical tunneling, the same reason that the sun shines.
The last question.
So, if we observe a black hole through IR sensors, what do we observe?
Through what?
Infrared sensors.
Yeah, it would depend on the temperature of the black hole. If the temperature of the black hole is low enough as to emit heat, then you will see the radiation coming from the black hole. Whereas if it is at a very wide black hole, your filter will take it out, and you will not see it, or you'll see a small amount of.
No, like the particles are coming out.
Yeah.
It will have a certain kinetic energy.
Right.
And that kinetic energy can be inferred to as heat.
Yeah. In any thermal spectrum, there'll be a part of the spectrum which is in the infrared, and you'll only see that part. You will not see the rest of it. That's my answer. If you have a filter, you will only see what you want to see, right, through the filter. If you have a red filter, you'll only see, I'll look at the tube light, I'll see red. So that's no different between a black hole and a tube light or anything. Okay, I think.
So with that.
Sorry, there was a question here. I'll just finish this one. He's been waiting for a while. Yeah.
Does global warming and black hole theory has any relevance where we can destroy the plastic? The application of black hole can be used for global warming, or it has nothing to do with the
Actually, in order to use a black hole practically, we have to get one first. We have to find one, no? And to make million solar mass black holes is not so easy. To make even solar mass black holes is not so easy. We have to make a small, tiny black hole that we can use for our own convenience, and we haven't done that yet. I was making these points in a slightly dramatic way in order to get these points across. It's okay, no? For scientific communication, it's okay.
Good. It will be more interesting for listeners in the way you said it.
Right.
Okay, so with that, let's thank Professor Samuel for a wonderful talk.